In this video, we'll see the temperature stresses induced in composite section. Now the composite section is shown in the figure. There are two materials, 1 and 2. Alpha 1 is greater than alpha 2. Coefficient of linear expansion of material 1 is greater than that of material 2. In other words, when the individual materials they are heated to the same temperature difference, then material 1 will expand more as compared to material 2, and that is shown in this second figure. So you can see, if we consider them separately and if they are subjected to the same temperature difference, then this first material will expand more because its coefficient of linear expansion alpha 1 is greater than alpha 2, and second material will expand less as compared to that of material 1. But when they are heated as a composite section, then they are able to expand up to this particular level. In other words, this material 2 will be in tension because it has to expand up to this point when it is acting as a composite member, whereas the material 1, which is having the more value of thermal coefficient of linear expansion, will be in compression because it has to be compressed up to this level. Okay, so whenever the material is having higher coefficient of linear expansion, that particular material is in compression, whereas the material which is having less coefficient of linear expansion, that will be always in tension when they are acting as a composite member. Now this is the expansion L alpha T of material 2. So this is the free expansion of material 2. This is the free expansion of material 1, that is L alpha T1. X1 is the amount by which it is to be compressed so that it will come to this position, and X2 is the expansion by which this particular bar 2 is to be stretched so that it will be in this particular position. So we can say that the total expansion, total elongation of bar 1 is equal to total elongation of bar 2, because ultimately they are going towards the same final position when they are acting as a composite member. These are the cases when they are acting as a separate member. So we can say that L alpha T1, so that is this particular one, minus X1 will give you this position, is equal to L alpha T of 2, that is this plus this plus X2. So this is the total elongation of bar 1, that is the left hand side, and total elongation of bar 2. Now X1 and X2, they are nothing but our delta L or deformation, that is PL upon A of 1, and here also it is PL upon A of 2. So L will get cancelled out throughout because it is common. So this L we have cancelled in the next step. So L will get cancelled out because it is common throughout all these particular terms. So it is alpha T of 1 minus P upon A of 1 is equal to alpha T of 2 plus P upon A of 2. In other words, it is alpha 1 into T, where T is the temperature difference, minus sigma 1. Now P upon A is sigma, that is stress. So therefore P upon A is nothing but sigma 1 upon E1 is equal to alpha 2 into T plus sigma 2 upon E2. Now transfer this alpha 2 into T on the other side. So it is alpha 1 T minus alpha 2 T is equal to, transfer this minus term on this side, it will become positive. So it is sigma 1 upon E1 plus sigma 2 upon E2. Take T common, so it is alpha 1 minus alpha 2 into T is equal to sigma 1 upon E1 plus sigma 2 upon E2. In other words, we can say that delta L for elongation of bar 1 will be equal to L1 alpha 1 T, that is this particular first term, minus X1. X1 is sigma 1 L1 upon E1, that is P upon A is sigma. So it is sigma 1 L1 upon E1. Similarly, delta L for the bar 2 will be equal to L alpha T plus X2. So L2 alpha 2 into T plus X2. X2 is P upon A is sigma. So it is sigma 2 into L2 upon E. So this is the expression for total elongation of bar 1 and bar 2, and this is the final expression in terms of temperature, stress, modulus of elasticity, and coefficient of linear expansion. Suppose we want to find out what will be the temperature stresses in members in series. Again, it is the case of composite section. So the previous was the case of parallel. Now, free expansion in this particular case will be equal to L1 alpha 1 T plus L2 alpha 2 T. Now, this thermal expansion of these two bars is prevented by this end supports. So we can say that, let us assume that support reaction is equal to R, and that is equal to P1 is equal to P2. So deformation due to the reaction. So this reaction will offer some deformation to this free expansion, and that is nothing but delta L1 plus delta L2. So that is PL upon A of 1 plus PL upon A of second part. So P upon A is sigma. So it is sigma 1 L1 upon E1 plus sigma 2 L2 upon E2. Now free expansion is equal to deformation due to reaction, because as the expansion is prevented, whatever the free expansion it tries to do, the reaction will offer the opposite deformation, and the bar will remain in the same position. So we can say that L alpha T of 1 plus L alpha T of 2 is equal to sigma 1 L1 upon E plus sigma 2 L2 upon E2. So this is the temperature stress in case of composite section. Now, if the supports are slightly moving or if they slightly deform, then that is known as the yielding of the support. So in that particular case, free expansion minus gap will be equal to deformation due to reaction. So whatever the gap that will be given in the example, that you can substitute that value and you will get the final expression, which is similar to this. Only thing is that on the left hand side we are having this minus gap term. Now suppose we are having, now let us solve this example. Suppose we are having a steel rod of 30 mm in diameter and 1 meter long, and it is heated to 100 Kelvin. Now temperature difference in centigrade and Kelvin is same, so there is no need of any conversion over here. And at the same time it is subjected to pull P. So not only that it is heated, but it is subjected to pull P also. So simultaneously there will be a free expansion and there will be a deformation due to load P or pull P. If the total extension of the rod is 2 mm, that is the expansion, thermal expansion or free expansion, and the deformation due to pull P, that total extension is 2 mm. What should be the magnitude of force P? Take alpha for steel as 12 into 10 raised to minus 6 per degree centigrade, and modulus of elasticity for steel material is 200 GPa. So let us write down the data first. Diameter is given as 30 mm, so area will be pi by 4 d square. Temperature difference is same in Kelvin and centigrade. P we have to find out. Length is 1 meter, that is 1000 mm. Total deformation is 2 mm. Alpha for steel is 12 into 10 raised to minus 6 per degree centigrade. Modulus of elasticity. Convert this GPa term into MPa. To convert GPa into MPa, we have to multiply by 10 raised to 3. So delta L1 will be elongation due to pull P, suppose, and delta L2 is elongation due to increase in temperature, that is free expansion. So delta L will be equal to delta L1 plus delta L2, that is deformation due to pull P plus thermal expansion. Now delta L1 is nothing but PL upon A, that is our regular deformation, and this is free expansion, that is L alpha T. Transfer this L alpha T on this side, it will be minus L alpha T, and that is equal to PL upon AE. So we can say that transfer this L upon AE term on this side. So here it is L upon A. On this side it will become a reciprocal of the term, that is AE upon L, and we have kept only the term P on this side. So this L upon AE term, when it comes on left hand side, it will be AE upon L, that is a reciprocal of this. And now substitute all the values and make the calculation. So you must get this value. So check these values whether you are getting this value 113.1 into 10 raised to 3 Newton or 113.1 kilonewton or not. Now suppose we are having a copper bar AB whose length is 600 mm and it is placed in position as shown in the figure, and it is a triple circuit box. That is the application which is mentioned, and it is at room temperature with a gap of 0.3 mm between end B and rigid wall. Calculate the axial compressive stress in the bar if the temperature rises to 60 degree centigrade. Take alpha for copper as 17 into 10 raised to minus 6 per degree centigrade and modulus of elasticity for copper as 120 GPa. Assume room temperature as 25 degree centigrade. So length of the rod is 600 mm, that is L is given as 600 mm. Then gap is 0.3 mm as indicated in the figure. T1, that is the room temperature, is 25 degrees centigrade. T2 final temperature is given as 60 degrees centigrade. So change in temperature is T2 minus T1, that is 60 minus 25, that is 35. Modulus of elasticity for copper is 120 GPa. So it is 120 into 10 raised to 3 megapascal. Alpha for copper is 17 into 10 raised to minus 6 per degree centigrade. Now free expansion of the bar is L alpha T, and delta L will be equal to free expansion minus the gap which is given to us. So L alpha T minus gap. So substitute all the values, that is L, alpha and T. All these values they are known to you. Minus gap, that is 0.3 mm, and that value comes out to be 0.057 mm. Now strain is equal to change in length divided by original length. That value also you can calculate. And then sigma will be equal to E into E. That is modulus of elasticity 120 into 10 raised to 3 into E. That is linear strain 9.5 into 10 raised to minus 5. And that value is 11.4 megapascal. So this stress that is induced in this bar will be a compressive stress because expansion is prevented in this particular case.